Modal analysis, fatigue analysis, and optimization of drop arm using FEM. Abstract: the drop arm is part of the steering component in a tractor. It is connected to the sector shaft and moves in angular motion with the help of the sector shaft. This motion causes the wheels to move left or right, depending on which way the steering wheel is moved. It is important you have your drop arm in good working condition because poor steering can be hazardous to you and those around you. A performance study will be carried to perform failure, fatigue and modal analysis of pitman arm using Ansys. The structural optimization will be done on the drop arm by changing the structure of pitman arm by modifying the geometry where stress values are critical. The meshing and boundary conditions will be applied and analysis will be carried out using Ansys 16.0. Keywords: finite element analysis, fatigue analysis, modal analysis, drop arm, FEM. Introduction. The drop arm is a steering component that is used in an automobile or tractor. It is a linkage between sector shaft of the steering box and drag link. It transmits the angular motion to the linear motion that is required to steer the wheels in desired direction. The arm is attached to the sector shaft and supports the drag link or center link. It transmits the motion it receives from the steering box into the drag link, causing it to move steering arm to turn the wheels in the appropriate direction. The track rod is attached between the opposite sides of the steering arms. A damaged or loose drop arm can cause inability to steer, wandering to the left or right while on the road, poor steering. 2 objectives. To perform 3D scanning of drop arm used in tractor. To perform failure analysis of drop arm. To analyze the fatigue life of the component. To perform modal analysis of the component. Structural optimization for better design and increased efficiency. 3 Methodology: Phase I Literature Survey. Phase 2 3D Scanning and CAD Modeling. Phase 3 Failure, Fatigue and Modal Analysis of Drop Arm. Phase 4 Optimization of Drop Arm. Phase V Failure, Fatigue, and Modal Analysis of Optimized Drop Arm. Phase 6 Validation and Report. 4 Literature Survey. Pradeep B. Patil ETAL1 Static and Modal Analysis Results of existing pitman arm proved that the model is more stable and there is scope for optimization. The comparison between modal analysis results of existing and optimized pitman arm has been performed and it is observed that the pitman arm is vibrationally stable. Sijith PM ETAL2 performance study is carried out followed by static structural analysis and optimization to minimize the weight of the pitman arm and thereby reducing the material cost. Optimized model is then verified by physical testing. Vimal Ra Aparo ETAL3 has investigated 2 DOF mathematical models of pitman arm steering system and derived using Newton's law of motion and modeled in MATLAB/Simulink software. The performance of the electronically actuated pitman arm steering system can be used to develop a firing on the move actuator, FOMA, for an armored vehicle. Srilekha Orala, G. and Gopala Krishna 4 has presented the static and modal analysis of steering lever link of a tractor to check its deformation, maximum stress and natural frequencies by using 3 materials. Aniket Kolkar ETAL5 has designed and fabricated the fixture which is used in the manufacturing of pitman arm of steering system. The fixture is designed by using software Kashif 5R21. The purpose of the fixture is to provide strength, holding, accuracy and interchangeability in the manufacturing of product. The main purpose of a fixture is to locate and, in the cases, hold a workpiece during an operation. Shatabdi Sonawane ETAL6 static analysis results of existing pitman arm proved that the model is more stable and there was scope for optimization. The pitman arm is optimized. The weight of original model is 974 gm and that of the optimized model is 840 gm. Weight of the component is reduced successfully up to 14% after optimization. The study confirmed that optimized pitman arm is structurally stable with good fatigue life. Pradeep B. Patil ETAL7 based on FEA it can be concluded that the optimized pitman arm has infinite life because it can withstand above 10,00,000 cycles. Weight reduction of 9.04% is obtained without compromising the strength of pitman arm. Natural frequency of both conventional and optimized pitman arm is extracted. V3D scanning and CAD modeling. 2. Discretize the model by meshing. 3. Define the element type, S, to be used. 4. Define the material properties of the elements. 5. Define the element connectivity. 6. Define the physical constraints, boundary conditions. 7. Define the loadings. 8. Solve the analytical problem. 9. Result evaluation. Finite element analysis is a computational technique that is used in engineering to obtain approximate solutions of boundary value problems. The following are the steps for pre- and post-processing in FEM. Property. Value. 6. Force calculations. Total mass of the vehicle. M1 equals curb weight plus driver weight plus tractor implement weight. M1 equals 1713 plus 80 plus 1000 equals 2793 kilograms. This weight is divided into front axle weight and rear axle weight. 35% of the total weight is taken by front axle and 65% is by rear axle. Therefore, mass on the front axle. M2 equals 977.55 kilograms. Mass on one of the front wheels, M equals 488.775 kilograms. Width of tire, B equals 132.08 millimeters. Center of rotation, kingpin, to wheel, E equals 145 millimeters. Coefficient of friction, equals 0.7. Distance from kingpin center to tie rod pin, L1 equals 195 millimeters. T equals torque required to rotate one wheel, torque at kingpin. Since single steering arm will be handling two wheels, so the force on steering arm will be doubled. S equals maximum bending stress. Equals bending moment. Equals vertical distance away from the neutral axis. Equals moment of inertia. Stress plot. Maximum stress, 205.7 MPa. Minimum stress, 0.0056274 MPa. Ultimate strength, 450 MPa. Maximum force component can withstand, 11,472.026 N. As stress is well within the limit and deformation is less, hence there is scope for optimization. 8. Fatigue analysis of drop arm. Results for fatigue analysis. Force applied, 5,244.0666 N. Fig. 9. Fatigue life of drop arm. Minimum fatigue life, cycles 23,122. Maximum fatigue life, cycles 1 times 106. Fig. 10. Damage of drop arm. Minimum damage, 1,000. Maximum damage, 43,248. 9. Modal analysis of drop arm. Modal frequency results of 6 modes of drop arm calculated in Ansys 16.0 are as below. X. Optimization of drop arm. The optimization of drop arm is done by modifying the geometry of drop arm where stress concentration is highest and lowest. Drop arm is optimized by modifying stress concentration areas and improving geometry for better stress distribution. Extra material is added on top side of drop arm to provide better stress distribution in Z direction, and extreme edges are smoothened. A slot is also added in low stress areas to compensate for increased weight and netter stiffness in Y direction. The optimized geometry as below. Maximum stress, 185.24 MPa. Minimum stress, 0.000548878 MPa. Ultimate strength, 450 MPa. Maximum force component can withstand, 12,738.886 N. 11. Fatigue analysis of optimized drop arm. Results for fatigue analysis. Force applied, 5,244.0666 N. Minimum fatigue life, cycles 33,957. Maximum fatigue life, cycles 1 times 106. Fig. 14. Fatigue life of optimized drop arm. Fig 15. Damage of optimized drop arm. Minimum damage, 1000. Maximum damage, 29,449. 12. Modal analysis of optimized drop arm. The modal frequency results of 6 modes of optimized drop arm calculated in Ansys 16.0 are as below. Modal frequency. Optimized drop arm. First mode. 902.39. Second mode. 1574.9. Third mode. 3761.5. Fourth mode. 4497.9. Fifth mode. 6230.7. Sixth mode. 8561.1. Table 4. Modal analysis of optimized drop arm. 13 results and discussions. Fatigue analysis. Parameter. Drop arm. Optimized drop arm. Min. Max. Min. Max. Fatigue life, cycles. 23,122. 1 times 106. 33,957. 1 times 106. Damage. 1000. 43,248. 1000. 29,449. Table V. Comparison of fatigue life. Structural analysis. Parameter. Drop arm. Optimized drop arm. Min. Max. Min. Max. Equivalent. Von Mises, stress. MPa. 0.0056274. 205.7. 0.00548878. 185.24. Equivalent elastic strain. mm/mm. 4.0917 times 10-8. 0.0011. 4.1071 times 10-8. 0.00089992. Ultimate strength. MPa. 450. 450. Maximum force component can withstand, N. 11,472.03. 12,738.886. Maximum deformation. mm. 0. 0.63854. 0. 0.60859. Table 6. Comparison of structural analysis results. Modal analysis. Modal frequency. Drop arm. Optimized drop arm. First mode. 896.86. 902.39. Second mode. 1560. 1574.9. Third mode. 3617.4. 3761.5. Fourth mode. 5047.1. 4497.9. Fifth mode. 6004.2. 6230.7. Sixth mode. 8284.4. 8561.1. Table 7. Comparison of modal analysis results. 14. Conclusion. Static and modal analysis results of existing pitman arm proved that there is scope for optimization. Von Mises stress in optimized drop arm is reduced by 10%, maximum force drop arm can withstand is increased by 11% and deformation is reduced by 5% under same loading conditions. The comparison between fatigue life results of existing and optimized pitman arm has been performed and it is observed that the pitman arm is having infinite life. The comparison between modal analysis results of existing and optimized pitman arm has been performed and it is observed that the pitman arm is vibrationally stable. The above study confirmed the optimized pitman arm is vibrationally and structurally stable with good fatigue life.